Robin, just confirming, so sharing doesn't work for you at the moment.
Yeah, I can't share at the moment. If it's not looking like we've got a imminent solution, I guess I can at least start my talk without slides. But I've got an introductory section before we get on to any sort of demos. But we'll give it one more minute to see if we can resolve this because it would be better with visuals.
You're on mute, Nabil. I don't know if you
Sorry.
were.
Yeah, sorry. Rob, so Melanie had a question in the chat. So the question was like, if it's interactive, do you think it's useful if they follow along in an IDE?
So I haven't got sort of nice Google Colab notebooks or anything. So I would say that yes, you absolutely can follow along. So the hands-on element will be in two parts. One of them is there are some notebooks attached to the interpretability suite GitHub repo. So anyone who would like to feel free to clone and set up the repo to follow along. But I'd sort of more encourage that as a sort of after the session activity, because I can just share screen and we can go through the notebooks. But then there's also a demonstration with sort of web app interface, and I would definitely encourage anyone who wants to have a go to use that themselves. So there's no install required there. There's just a link, and it looks like I've just been
Yes.
made co-host as well. So we're in business. Right.
And I've just shared the link to the repo in the chat.
Brilliant. Okay, so hopefully everyone can see my screen now. Hi everyone, I'm Rob Davies, and I'm going to be running this session on the Interpretability Suite, which is the labs repository for everything interpretability. So yes, I'm a research engineer with CCAIM. So yeah, I've been working with the centre for just over the last 2 years. I've authored the library Datagnosis, which is our data-centric open source library all about hardness characterization and also the interpretability suite. I'm also currently the lead developer on SynthCity, which is our open source library, our biggest sort of open source community-driven effort, all about generating synthetic data, which there'll be a very hands-on session all about tomorrow. We'll go for a couple of hours working through notebooks together. But yeah, let's get on with the interpretability suite. So the sort of rough breakdown of the talk I'll do today is a brief reintroduction to interpretability. I wasn't aware quite how amazing Fergus's talk was going to be in covering all the areas, so I might skim over this slightly because you've literally just heard it, but I'll just raise some of the key points that I want to make about it, and then we'll move on to showing where the interpretability suite is and what it's for, and then the two demos that I mentioned before I could share my screen. So we'll look at creating some explainers with some notebooks, and then we'll use the web app interface to explore those explainers together. So this is the sort of traditional idea of behind interpretability. We've got data, a black box model, static predictions, and post hoc explanations of those predictions. And we obviously need to, these days, go much more beyond that traditional approach. So some of these methods you've just heard about. But yeah, we need things, we need methods for time series forecasting in order to understand patient trajectories. We need unsupervised learning methods to understand patient phenotyping, the heterogeneous effects estimations or individualized treatment effects based explainers to understand personalized therapeutics, personalized medicine. And there are also this idea of concept-based explanations, which yeah, can discover new clinical concepts. So yeah, what can be improved upon the traditional methods that the traditional approach that I just presented in the previous slide is we need to understand why features are or examples are important, not just which ones are important. And that can be seen much more when you have specific examples rather than general examples. We also need to understand when to be skeptical about a model. So which predictions are the predictions we need to be more skeptical about? Because yeah, when you're using models in anger, yeah, for example, in a high stakes scenario, like in a clinical setting, if you've got an individual patient walking into your clinic and you give a predicted, a prognosis prediction to them, you need to be very sure whether you trust the model's prediction in this one specific case as well as overall. So yeah, there's definitely that idea about when to be skeptical. And then also we need to keep humans in the loop much more than in the traditional approach. We need to adapt our explanations to the user's knowledge. So yeah, that's saying basically we need to go from this situation where you've got a patient, Bob, you've got a black box model, a prognostic prediction, where perhaps the patient is an American patient, but your black box model has been trained on British data, and all you've got is generic, yeah, all you've got is these generic post hoc explanations. We need to go from that situation to something like this, where if you've got an American patient, an American clinician, how do you get that sort of change in context into the explanations and things become personalized and much more specific? So this is a screenshot from the interpretability suite. So this shows the table that we have of all of the different methods that are included in the suite with links to the source material in terms of the source code and the papers. You can see we've got lots of different methods all included as well, mostly from our lab, but also a few from the wider community as well, wider ML community, just so they sit together in the same place and you can compare and contrast and understand them. And yeah, there are different cases where we need to use different explainers. So there are models for explainers for tabular data and for time series data and unsupervised models or individualized treatment effects. But there are also different models, or different models also produce different types of explanations. So that's things like feature-based explainers and case-based explainers and concept-based explainers. So all of that information is there in the in the interpretability suite. I wanted to talk briefly about simplex in a bit more detail, just because it's quite a nice example that couches the a few of the different ideas together. But yeah, as Fergus has gone over this in some detail, I think I'll whiz through it a bit more quickly. But it's useful for the demo later. So basically, to go over it again, you have a feature that exists, or you have an example that exists in some space. You have apply a black box model, it produces a prediction Y. We can provide our own corpus of examples that we can also apply our black box model F to get its own predictions. And what we're doing in this case is we're looking at that latent space one step back from the final model prediction, where we can compare our corpus to our individual example in that potentially higher dimensional latent space. and we get outputs like this. And so we can see that in the top half where we're looking at the digits, we can see our example has been given, we've got that individual test example there, that's been given a predicted value. And when we've compared it to all of the members that we've provided in the corpus, it breaks down as being 46% similar to the first one, 37% similar to the second, 17 to the third. You can see for each member of the corpus, if you're using historical examples where you have the genuine label, because as Fergus said, you're providing your own corpus. So you do have the ability to provide historical data, or in terms of a clinical setting, you would need them to be historical in order to have the genuine label. But in the case of MNIST, you can just, you have access to the genuine label. But you can see in the examples from the corpus that it's used in the mixture explanation, you can see what is the label that's been given? Does that match the image that you see there? Do you agree with the label for all of the members of the mixture that are important to the explanation? That's one indication that for whether or not you agree with the prediction on your test example. And then there's also the idea of are all of the members of the mixture the same in terms of in terms of the label and in terms of the prediction. If there's any confusion there, that's all indication that you might be more skeptical about the prediction on your test example. And if that seems super obvious in this case, where you're looking at numbers and you can just see that they're all the number 3, hopefully in the bottom example of clinical risk estimation, where things become much more complicated, why this is valuable. When a clinician provides a corpus of previous patients that they're familiar with, they can use the individuals that come up in this mixture explanation to understand the context behind their new patient, for whom they don't have any of the backstory for, because it's not a historical example. We don't know the genuine outcome yet, but we can see, yes, okay, our example, our test example, our person who's walked in the clinic is 58% like the first example and 25% like the second historical example. And we can see, do we trust that? Do we trust the model? But simplex is interesting because it is primarily an example-based explainer, but not exclusively. We do also have this feature importance as well. And so that's really nice. We can see the red and the green highlighting here to show which individual features are important to the model. And that sort of, in combination with the example-based explanation, gives us a lot more information about whether or not we should trust the prediction. We can see that not only are the ages relatively similar in the clinical risk estimation here, we can see that that's actually not super important to the model, whereas the fact that in the first 2 examples from the corpus, they've got the same grade, prostate cancer in this case, as the test example, that is a much more important feature. So we're considering the similarity there to be more important than the similarity elsewhere. And so just a final slide on simplex then. What's so special about simplex? It unifies the example and feature-based explanations, which together brings, I think, a lot more power than either of them individually. And it also captures the insights from the model's latent space. And so you're not just comparing on that surface level, you're actually almost like peeling back the outer layer of the model to peek inside to see what was how did the model see the corpus compared to the individual example. And then it's also keeping humans in the loop because because the user brings the corpus, that allows the explanation to be couched within the terms of the understanding of the user. And so from there, let's jump on to doing some bit more hands-on demo. First of all, if I take us to this page, this is the interpretability GitHub page. I think there's a link in the chat now. And so I'd encourage you to take a look at this. There's lots of great information here. But I'll just sort of orientate you as to what we've got. There's a bit of background with some useful links. There's another introductory video that you can watch. There's the interface, which we'll go over as the second part of the demo. And then there's these tables that I showed in the slide deck. But also, I just wanted to draw your attention to the flow diagram here, which I think is super useful. Because as I showed with all of the tables in the slide deck, we've got lots of different types of explainers and lots of different types of explainers in terms of the type of explanation they give, and also lots of different contexts and data modalities. That not all models, not all explanations are applicable to all cases. So there's the flow diagram here. You can sort of roughly follow down, like, what's my data like? What type of explanation am I looking for? And you can find the method that's right for you. And then the other thing that's present in this repository is there's a simple sort of Python interface that allows you to use any of these 4 methods here: simplex, dynamask, shap, or symbolic pursuit, with the same interface. So it's a common interface for all 4 methods that just makes it a little bit easier for you to get your hands on and explore what's going on and how to use each of these methods. Perhaps if you are really interested in one of these methods or one of the other methods, you'd want to go away and implement from scratch for your specific use case. But this is just sort of bridging that gap to allow you to get results much quicker. And so it follows a sort of familiar kind of design pattern from things like scikit-learn, where all you need to do is initialize your explainer object, then fit that explainer. And once you've got a fitted explainer object, you can use it to explain data points and produce summary visuals with the summary plot function. So I think that's enough for an overview of what we've got there, and we can jump into some tutorials. So there's a tutorial for each of those 4 methods, and there's in fact 2 tutorials for simplex, one for tabular data, one for time series data, because simplex is also another reason it's so amazing is it can work for both modalities there. And so, in fact, as we've talked about simplex quite a lot already today, let's jump into the dynamask example, perhaps. And I'll talk you through how you create an explainer using our interface here. So first of all, for anyone who wants to follow along, feel free by cloning the repository, but it's fine just to follow on screen here. All we need to do is we make our imports of our standard libraries, and then there are a few things that come with the interpretability suite here. One is I've just defined a very simple RNN that works with the data, but you can use any of your own PyTorch model. This is just something super simple. I'd encourage you, go away, create your own model, train it, and do any of that work that you want to do to personalize the tutorial. But because we're not really interested in actually the model's predictions but for this case, what we're interested in explaining them, I've just got a simple example set up for you, so you don't need to do any of that work. Then we need the dynamask explainer itself, and then also there's just a simple input-output utility thing that we can import that helps load and save our models. So then I'm just going to load a data set. It's fairly standard time series data set. This one's not super interesting. And then if you do want to follow along in your own time, or now, you will need to go to this link to download the trained model, because we don't want to wait for it to train here. You can just save it in the repository under resources, saved models here. and then the notebook will run. But yeah, all we're going to do is load the model from that saved file. And then we're going to initialize our model. And you can see a few things we have to pass to initialize Dynamask. First, it's the PyTorch model itself, and then it's the perturbation method you wish to use. So Dynamask is, yeah, it is a perturbation-based model where you will receive different results if you perturb the system in different ways. And these are the 5 different perturbation methods available to you. I think, yeah, if you don't want to go super deep, yeah, something like Gaussian blur will like absolutely do the job for you. But yeah, they all have slightly different yeah, pros and cons. And yeah, if you really want to get into the nitty gritty, then I would encourage you to go to the paper and explore the individual examples here in more detail. But yeah, we can just pick a simple Gaussian blur here. And we've also got, yeah, grouped or not, but yeah, let's just keep it simple. So yeah, we've initialized our explainer, and then all we need to do is to fit it. And so it will take a few seconds to, there we go, fit our explainer. And once we've done that, all we then need to do is to, yeah, explain, yeah, myexplainer.explain, and there are yeah, a few extra parameters here that we can go through in a bit more detail later. But and we can create a summary plot. So here we've got features on the y-axis. The data set we're looking at only has one feature, and there's the time steps showing that, in fact, in this simple data set, it's very boring, and all of the early time points for our simple model, our simple model is just not looking at them whatsoever, and everything is super important on the right-hand side. So the later half of the time points. Finally, you can save the models with io.save explainer, just passing the explainer object itself as well as the path that you want to save it under, and you'll create that saved object. And so, yeah, it goes for the same for all of these tutorials that are all available on the GitHub. And I would encourage you to run each of these that you're interested in exploring in order with your own data, with your own model, and you will be able to create this saved explainer object, which you can then, in fact, load up into our web app interface. So let's move on to that part of the demo now. Here's the landing page for the interface. I will actually just copy into the chat now, for anyone who wants to have a look, the direct link to the page. It is also available on the it's available on the interface on the GitHub here. If you there's just a hyperlink here. If you're already on the GitHub, you can click that to go straight through as well. But yeah, here we are on the landing page of our web app. We can see we've got the same 4 methods available to us in this, and using this web app just gives us a bit more interactivity to properly explore the explanations. It's just much nicer than the static situation in the notebook. So, as I said, you can upload your own explainer here. On the upload explainer tab, there's just a drag and drop for you to explore. I'll just show you the examples that come preloaded in the web app today. But yeah, I would definitely encourage you to explore that in your own time. So yeah, for simplex here, you see we've got, we can select tabular or time series. Let's just start with tabular. We've got options of different data sets and different models, all of that, if you were uploading your own, you can choose, either of the data types. You can choose any data set you want. You can have any PyTorch model you want, and it will all be compatible. The fact that we've just got a few drop downs here shows you that, yeah, we've got all that flexibility available to you. And then I've also just included this little sort of expander here that explains whatever data set you're looking at. Hopefully everyone's fairly well versed in the iris data set, which is the one we're looking at now. So it's not as interesting as for some of the more obscure ones. But yeah, here's the main interesting area of the interface. We've got our test record that we're looking at. We can select with this scroll bar. So we've got a few, well, we've got 20 different test records in our data set, and we can explain the predictions for any of them using our corpus. I think we've got a corpus of 100 examples here. But you'll see at the moment, we're only seeing 4 examples because we've set a simple threshold on the example importance. So at the moment, we're seeing anything with an example importance of greater than 5%. And that's also configurable. If I set that to 0, suddenly after a second, you see we can see everything. But all of the examples down here, yeah, you can look at them if you want, and they are providing 0.02% of that sort of mixture model. It is pulling towards corpus number 83 by 0.02%, but yeah, not super enlightening. So if we raise this back to something sensible, we can just see the examples that are important to us. And then in the same way that we were comparing in the slide, and I'm sure Fergus went through with you earlier, we can see every member of the corpus. What are its feature values we can compare to our test record? Do we think that our example here is 34% similar to this example and 22% similar to this example, etc.? Do we agree that our model should be seeing our test record as similar to a mixture of these records? And then also we're provided with the corpus prediction and the corpus label, as well as in this case, the test prediction and the test label. You wouldn't always have the test label in every scenario, but in this case we do, so it's available to us. We're not using the test label as part of any of the calculations under the hood. It's not put into Simplex when it's doing it, but it's just as we have it, it's useful to see when we compare to this. And actually, the sort of, yeah, there is maybe some reason to be skeptical of this prediction on this test record here, in that the records that it's similar to have different predictions and different labels. And so that's all playing into the explanation here, and maybe think maybe I am skeptical about these predictions, although maybe I'm wrong to be because it was right in this case. But you've just got all of that information, and you can compare and contrast the test record with the corpus. And yeah, you can go through each of the features in detail and decide yourself. Just very quickly, I'll show you what Simplex looks like when it's in time series. So it will take a little second to update because the data set is relatively large. But basically, you get an interface that looks exactly the same, apart from the table here is broken out into a few different tables, one for each corpus member, because we need the space for the rows to look at the different time points. If that's not, oh, there we go. Here, so here you see it's exactly the same idea. You can see the importance, the prediction, and the label above, and then the features with, we've got one feature here and all of the different time points. And yeah, we can look at different records and we can mess around with the threshold, but yeah, it's exactly the same. So hopefully that's all clear. I would just also draw your attention to the C code expander at the bottom. So for any of these methods, I've just provided a simple expander here with all of the code that was used to produce this saved model that I've loaded as an example. So if you want to use this demo app to look at any of these different things, and you want to use Dynamask or use Symbolic Pursuit or Simplex or whatever, to create something that looks exactly like this, then yeah, use exactly the code that's provided in the expander below, but with your own data, your own model, and you will be able to save an explainer and upload it. Okay, so let's move on to Dynamask, where we ran in the notebooks an example of how to save a model. This one's a bit more interesting, and we've got a few more features. And yeah, I just wanted to spend a second talking about Dynamask, and I think it's a super nice method. Um, it's a feature-based explainer, so it's not got the examples or the example-based explanations of simplex. But what it does do is it has really nice feature-based explanations per feature per time point. So you can select whichever test record you want to explain, and that's yeah, just to mention, yeah, we're selecting an individual test record that has a very specific personalized explanation here. So that's the specificity, the personalizedness of the explanations. And then we can, these other scroll bars up here will just like zoom in on different regions that you might be interested in. But let's look at the whole thing. And you can see that actually not only is, you get an idea that not only maybe that feature 3 is an important feature, generally maybe there looks to be a bit more green here than in some of the others, but also that it's relatively, well, it's more important in the first half than the second half, but there are still regions where it's important throughout the whole time space, whereas something like feature 0, that seems to be super important around this sort of 30 to 40-ish time period, and maybe a bit before as well, much more than later on. And then if you're looking at this, seeing like these hard stripes of, well, you know, this, how can something be very important, very unimportant, very important, very unimportant, etc. We also have this option to smooth the mask, which you can see from the little hover over there, just applies that Gaussian, temporal Gaussian filter to reduce some of that noise and give you a nice sort of general sense of the overall trend of the feature importance there, which I think, yeah, makes the picture a lot clearer, where you can see, okay, yes, it is actually very unimportant at the start, and there's this other period and much later on where it's very unimportant. And you can see the important regions really pop out a bit more easily. So yeah, that's Dynamask. If we have a quick look at SHAP, I'm sure you're all very aware of SHAP. It's one of the, ooh, that's absolutely typical. What's gone on with my live demo? Okay. But the issue with running demos absolutely live. If you just give me a sec, I'll try and get this up and running again. It's typical that it's been happy all morning. Something's gone down with the server. Excuse me 1 second. Yeah. Yeah, there's a question in the chat saying, are we overloading it? I think is the answer to the question. So if anyone does have it open and they can close it, I can try and see if it will reduce the stress on the little Streamlit system. But yeah, looks like it's not coming back at the moment, which is a shame. Obviously not done this talk with so many of you here before. So yeah, I will just I'll finish up without the live demo, and I'll just talk you through on the notebook, which is a bit of a shame, but no, that's the way with live demos, I guess. So I only had one more explainability method to talk to you about, and that was symbolic pursuit, which is a super nice method that unfortunately has some of the best visuals in the demo app, but there we are. But what I wanted to talk to you about was just, yeah, it's another example of how explainability can work. What we're doing with symbolic pursuit is, you know, once we've, you know, initialized and fitted our explainer, what we do is we create this here in this, you know, horribly formatted way, is a closed form mathematical expression which approximates the black box model. So instead of doing any sort of post hoc analysis of our model, what we do is we train this model to create, well, we optimize a closed form mathematical expression to approximate the model as best we can, and then hopefully we end up with something very similar to our black box model, which is completely explicit, and we can feed in the feature vectors here with the right weighting into that model, and from that we can extract our feature importance. And also, as Fergus alluded to, we can also, once we've got our closed form mathematical expression, we can actually perform a Taylor expansion on that expression in order to get interaction terms as well. So if you do a second order Taylor expansion, you not only get the feature importances, but the feature interaction importances. So you can see for like something simple like the iris data set that's in the demo, you can see like not only for an individual flower that you find is the petal width super important, but also the petal width in combination with the petal length is much more important than either on their own. And so you can really interrogate the data like that to discover what are the really important things, and that really helps with discovering how the model is using the different features, and gives some enlightenment on why individual features may be important. They're not as important on their own, but once they're in combination with other features. And that can be super useful in terms of understanding mechanisms behind situations. If you're in a clinical setting and you find that a particular feature is very important and you don't know why, but in fact it's really important in combination with other features, suddenly you might be inspired to think, okay, like there is a mechanism going on here where we've got this situation with feature one and feature two. There's obviously some sort of interaction going on there, and can be very useful in genuinely inspiring new research programs into why certain features are important, as well as simply just explaining your black box model. So I'm sorry we've not managed to reload the app so we can see that nicely for you all, but hopefully that's been useful in understanding how you can get a bit more hands-on with explainability from the lab. Hopefully you can spend a bit of time here and use some of these models yourself, create some explainers, and understand what's going on. And yeah, thanks very much, everyone. I can now open up the floor to any Q&A, any questions anyone has.
Awesome. Thanks so much, Rob. I can maybe help going through the ones in the chat, and then once we've covered the chat, then if anyone wants to check about anything. I guess, Simon, I might keep you a bit for later since it's specifically not on interpretability, but I note that I'm not forgetting you there. I know Miriam had a question, but it might have been during a demo.
Hi, can you hear me?
Yes.
Okay, yes, I saw in the demo that there was like the output when you were training the explainers was like error -0, and then I was wondering what was like the meaning of this. Maybe it's like a very specific question.
So the error in the log, like the error in the app that I was running, or
Yes, the error in the notebook. Sorry.
oh, in the notebook. Sorry, I didn't spot an error in the notebook. Can you remember which one?
In one
Oh,
of
so,
the first ones, I think it was.
okay.
I think it was like an error metric or something when you outputted like scores or values. It said like error 0.
All
Yeah,
right.
I think so too. But I was just curious, like what was, because I saw some metrics and then I was just like curious about like what was the specific purpose of it. But if it's too specific, it's okay. Like no
Yeah.
worries.
Yeah. I'm struggling to find. So yeah, that's in the so yeah when we were fitting the Dynamask. So each of the methods that we have, they're all solving their own sort of optimization problem. And so, yeah, we're reporting, yeah, the metric being the error in finding that sort of optimal solution for our explainer. So in the case of Dynamask, I can maybe show the paper, seeing as I have it open. Here we are. So here you see that this is the sort of optimization problem we're doing. We have our feature data set here, and we pass that to the black box model. We get our time series prediction out the other side, and we're calculating a loss here between that prediction and also this masked prediction, which comes from this initially randomly perturbed mask and this perturbation function. And so, yeah, the error is in fact just the loss here. So I think all that error 0 was saying was for our super simple data set that I was looking at, it managed to achieve an error of 0, which probably only speaks to the nature of the sort of toy data set I was using. I would be very surprised for you to find like the perfect mask solution for any more complicated data set. But yeah, that was the error that we're seeing in the notebook. It's the loss there.
Okay, thank you. Thank you very much.
No problem.
And then I'll just read the question to you, Rob. So Bettine asked just a clarification of what the corpus term refers to. Like, what is a corpus?
Oh, sure. So yeah, a corpus is just a collection of records. So people talk about corpuses of data being just like, yeah, a sort of small, perhaps in this case, but not always, but a data set. And in this case, what we're using it to do is it's a data set that, so if I talk from a sort of clinical data set perspective, maybe that makes it easier, but it is a general term. So if you have a clinician and they've got a patient who's come in, they are the test patient, they are the test example. You want to run your model to give a predicted value, a prognosis or something on this test patient. But in an example-based explainer, what we're trying to do is explain that prediction based on previous examples. And so the corpus is the much bigger data set that the clinician has access to from historical cases, perhaps. But it could be any data set. It could be, from a different hospital. It could be, a current data set from somewhere else with different context or whatever. But it's the whole data set that the user, in this case the clinician, provides to the explainer model that then the explainability model is comparing our test example to every single person in this corpus. And so if the clinician has provided historical examples that they're super familiar with, then when we compare our test example to everyone within that corpus and say, overall, our new test patient is 50% similar to person A from the corpus and 25 person B and 25 person C, they can see, okay, I know these three people and I can either agree or disagree that my new test patient is like that mixture of those three previous examples. But yeah, the corpus is just that whole data set where we're comparing our current test patient to this wealth of historical examples in this case. But yeah, it's just the data set that you're using for comparison. Hopefully that's clear.
And then Adrian asked just related to that.
Yes,
Adrian, if you wanna, I don't know if, or Rob, I guess, are you seeing it?
I can see it, but for the benefit of everyone, Adrian, you can ask the question if you are available to. Sorry, Adrian, I think you're a bit quiet, so I'll just read the question so everyone can hear. It's just on that note, is there any issue in drawing the corpus from the data the model was trained on, or is that reasonable? And I would say it's completely up to you. There is no issue with using the data the model was trained on, because all the corpus is doing is, it's just giving you that superset of people that you're familiar with that that give the most meaning to you. So there's absolutely no problem with using the data set, because it's just saying who is this new person similar to, and so there's no issue around data leakage or anything like that. And in fact, maybe the training set is likely to be the data set that you're most familiar with, but that's, it's also important to say it absolutely does not have to be the training set. The corpus can literally be anything.
I guess Rob Miriam has a question. So it's also corpus related.
Yes, I was thinking like a follow-up question that this type of corpus explanation poses challenges regarding privacy, and in the case like you cannot disclose the data set, the training data set. So how would you propose to deal with this?
So you're saying when you've got a private data set that you can't disclose the training set, how do you provide a corpus? Is that the question?
Yes, like in this case, like for example, there is a data set that was trained on one hospital and then they want to use it in a different hospital, say that like an example.
Yeah, obviously, in order to provide a corpus, you do need to have data from somewhere. And if that is, if the only data you have is protected by privacy and you can't send it to whichever party needs to run the explainability, that is prohibitive. But the idea of having the two separate hospitals is useful in that you may have a model that was trained on data from one hospital, but then you want to use it in another hospital. And so that second hospital presumably will have their own data set from their own patients that comes with the context of being, in Britain versus America or whatever. And so you can provide that corpus of local data. So you're not using any of that American data in the corpus. The only requirement for a corpus is that it exists in the same feature space. And so if you're collecting the same features as the American hospital, this British hospital can provide their own corpus from their own patients. And then by that way, they can get around, not needing access to the training data. All they need is the trained model and a corpus of people existing in the same feature space. But yeah, you are right in that you do need data from somewhere for sure.
Thank you very much. Thank you.
No problem.
And then I guess, Rob, there was not, I guess, an interpretability question, but it was a question from Simon, I guess, more generally, and I'll just paste it right below so you see it.
Mhm.
So I think it's more related to like autoprognosis and other things in the labs repo more generally.
Okay. Okay, yeah, I will have to go away and get the answer on that for you. I'm not, in fact, the lead developer on autoprognosis or on Tempor AI, which this question is about. The person that, the right person is Yevgeny Savelyev, who I think is also doing talks this summer school. But yeah, I'll happily reach out to him for you and pass on your question so that he's primed and hopefully can give you a good answer. But yeah, no, sorry, I can't provide you a good answer for that. It's yeah, outside of my software packages that I maintain.
Awesome. Thanks so much, Rob. And I guess if there isn't any more questions, you'll see Rob tomorrow for a much more in-depth version on synthetic data, which I know lots of people were interested on from Tuesday. So I think that'll be quite exciting.
Yeah, great. Thanks, everyone. And I will see you all again tomorrow for that. Thanks, Nabil.
Awesome. Cheers, Rob. And then we'll be taking a lunch break now between maybe for the next 25 minutes, and we'll be back at 1 p.m. with the next talk, which is machine learning for clinical trials with Javier Gonzalez from Microsoft. So see everyone then.